Hi, it's time for another math easy solution to discuss further into parametric curves and equations, and now look at calculus with parametric curves and go over tangents on this topic. So basically, if we look at calculus with parametric curves, having seen how to represent curves by parametric equations from my earlier videos, so make sure to watch those. I go over some crazy shapes and curves you can do with parametric equations. We now apply the methods of calculus to these parametric curves. In particular, we solve problems involving tangents, area, arc length, and surface area, but in this particular video we'll go over tangents. So let's jump in. So in my earlier videos we saw that some curves defined by the parametric equations x equals to f of t and y equals to g of t can also be expressed by eliminating the parameter, in this case t, in the form of y equals to, well, a function of x. In this case we'll call it capital F of x. And I'll go over the general condition under which this is possible in a later video, so stay tuned for that. So in this one, I'm just going to state that some curves you can do this when you're given parametric equations. You can remove the t parameter and get to y equals to a function of x. So if we substitute x equals to f of t and y equals g of t in the equation y equals f of x, we get, what we get is, well, let's just write this down. So if we have y equals to capital F of x, and now we replace this y with g of t, we get g of t is equal to, well, f of, and now this, I'll put a bracket like this, now this x, which equals to f of t, this equals to f of t, like that. So thus now if g, capital F, and f are all differentiable, meaning you could take the derivatives of it, then the chain rule for multiplication or for derivatives will be, and you could see, I'll put the proof of this in my video description box, so check that for proof. So it will get right here by the chain rule, if we take the derivative in terms of t, the time, for example, this one's going to be dg over dt. So the derivative is going to be g prime of t on the left side, and on the right side is going to be, well, we take the overall derivative of this f of t like this, and then by chain rule we need to multiply this by the inside derivative, which is going to be little f of t prime, like that. And now this equals 2 if we were to just remove this and write this as x, because that's just equals to x. So what we get is just, well, just to make it simpler, f prime of x equals to, f prime of x times it by f prime of t, like that. And the reason we're doing this is basically if we want to rearrange and then just write this as a derivative of this function of x, like that. So if now we make this not equal to 0, so if that's not equal to 0, and I'll write that over here, if f prime of t is not equal to 0, then we could move this over all the way to the other side, and then what we'll end up having is f prime of x is equal to, well, g prime of t over f prime of t, like that. And this is again if this is not equal to 0. And the reason it's not equal to 0, so when we move it over, you're not dividing by 0, which is undefined, or basically goes to infinity. It's just a vertical slope. And now what this is just the slope of the curve on a y-x axis. So since the slope of the tangent to the curve y equals capital F of x at the point x and capital F of x like that is simply y equals f prime of x, which is this over here, the equation above enables us to find tangents to parametric curves without having to eliminate the parameter. Because notice the parameter is right there, so we don't need to remove it, and we can still find the derivative of the function as a function of x, like that, which is quite amazing. So what we could do is, using Leibniz notation, we can rewrite the above equation in an easily remembered form. And one thing we should note is, well, this g of t, this is the same thing as writing, well, remember the g of t, y equals g of t. This is y prime of t. So when you write y as a function of t, which is y equals to g of t, and then x equals f of t. So when you have x in that one, this is the same thing as writing here x prime of t, like this. And Leibniz notation, I'll put the link below for Leibniz notation. Basically, it's writing this in terms of, instead of writing this right here, this is, remember, this equals to y. This is y prime, and this is in terms of x, like that. And I'll write this down here. y prime of x equals to this. And this one's y prime of t. So when we write it in that notation, Leibniz notation, we write dy over dx equals 2, and this equals to now the derivative here in Leibniz notation, that's just dy over dt. So this is going to be dy over dt all over, now this one is going to be dx over dt, like that. And this is again if, and I'll circle this, this is if we have dx over dt, which is just our f prime of t, like that. That's the same thing over there. That's if the bottom one here is not equal to 0. So dx over dt is not equal to 0. So otherwise we'll have an undefined derivative. So if this is true. And instead, yeah, we could just circle this entire thing together. So like that. And now a note I want to make is if we think of a parametric curve as being traced out by a moving particle, which is a good representation, which I've gone over in my earlier videos on parametric curves, then if it's a moving particle, then dy over dt and dx over dt are the vertical and horizontal velocities, or the speed of the particle. And the above formula says that the slope of the tangent is the ratio of these velocities. That's quite amazing. Yeah, so a good way to visualize this, if you have, let's say, x and y coordinates like this over here, and you had a parametric curve such as this, and you had a particle over here, and it's moving around this direction. Let's say it gets to the point here, and now basically the tangent line across this would look something like this dashed line, like that. And now basically if the point is over here, and let's say we had a dashed line across like this, and now we have the slope, let's say m over, let's say a unit of 1. This one's the slope. That's going to be, well, our dy over dx, and this is going to be equal to the ratio of the horizontal component of the speed of this particle, which is going to be, and I'll move this over. So I'll move this over here, this m, and I'll put this m like that as for slope. And now this point right here is our dx over dt. So with time, how fast it's moving, and then in the vertical direction, this is dy over dt, like that. And then there's basically the slope like this is equal to dy over dx, and that's going to be the ratio of these two. So dy over dt over, so the vertical over the horizontal velocity components. So yeah, that's just a good way of looking at it. And again, the particle moves at different speeds, as I've shown in my earlier videos, so make sure to check those out. And now what I want to state is that it can be seen from the above equation that the curve has a horizontal tangent when dy over dt equals to 0. That's basically if the horizontal one, the vertical component is, if this is 0, then what we end up having is a flat line. So this becomes 0, and then so it's not moving up. We end up getting a flat line, which is the same as dy over dx equaling to 0. So basically, horizontal tangent. This is dy over dx is 0, just a horizontal line, provided that dx over dt is not 0 as well, otherwise you have an undefined. And we'll need to use limits, etc. to do that. And also it has a vertical tangent when dx over dt is 0. So for example, if the bottom one's 0, this means we have, well, an infinite slope which is going vertical up like this. So that's going vertical up like that, again, provided that the dy over dt is not 0. So you don't have a 0 over 0 scenario. So this information is useful for sketching parametric curves, as I'll go over in some examples in later videos, so stay tuned for that. So, and as we know from earlier videos on curve sketching, it is also useful to consider the second derivative, which is useful for acceleration, or basically how a curve is curved. And this is by the second derivative test, and I've gone over my earlier videos, put a link on curve sketching for that. And this is the second derivative d2 over d2y over dx, squared like that. That just means the second derivative. And this can be found by replacing y with dy over dx in that above equation. So we have this equation, dy over dx equals to dy over dt, and this is dx over dt like that. I just want to write this down here. So if we have dy over dx, now this equals to, well, dy over dt over dx over dt. I just want to write this to show you, to be clear so you don't make any mistakes on this. So the second derivative is, well, this is going to be the same thing as, right, I've taken derivative twice. This is d over dx of this dy over dx, which is the same thing as writing d squared over dx squared y like this. And this means what we end up having is we put this dy over dx inside this y right here. So then we just replace y with dy over dx, and then also this y gets replaced now with this dy over dx. So we need to be very careful in this. So when we do that, what we end up having is, well, a d over, well, dt, and now we replace this y, which is going to be a dy over dx. So we're taking a second derivative, and the bottom just remains the same, because all we're doing, the only thing changes is this y. The same thing, this is the same thing as writing it like this, so that just means, yeah, we just plug in dy over dx inside y, like this. So this is what we have, and I wanted to make this clear so that we don't make the mistake where, well, note, so be careful, note / warning, let's put a warning like this. This is very important, you don't make this mistake. So warning, if you can't just go d2 or dy or the second derivative like this, dx squared. You can't just, this is not equal to, well, just casually writing d squared over dt squared, or the second derivative of y in terms of t divided by this right here. This is going to be x dt squared like that. So you cannot do this. Yeah, let's move this over here. So you can't do this. You can't just write the second derivative is equal to, well, the top derivative in terms of the second derivative of y in terms of t divided by the second derivative of x in terms of t, because that's not the way this works. Notice how to even determine this, I had to basically use a chain rule, etc., and get to this. And now that we have this, we could just, the way to do it is just to replace y now with dy over dx, because the second derivative is the same thing as writing this, which is pretty interesting. Yeah, so again, I make sure, I can't stress this enough, do not just do this randomly. That's not how derivatives work. Anyways, that's all for today. If you learned from this, pretty interesting video on determining tangent lines. And again, now that we have this, we can determine the tangent line or the tangent to the curve y equals capital F of x without needing to eliminate the parameter. So we could just use those parametric curves to help graph it on an xy axis or xy plane. And also in a later video, I'll go over the general condition on which this is possible to switch to eliminate the parameter, in this case t, because it's not always possible, but I will show that in later videos, so stay tuned for that. Anyways, that's all for now. If you learn, like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another math easy solution.